Physical verification of curved designs offers many challenges. Using methods made for Manhattan structures on curved designs is complicated and not always reliable. Calibre's marker shape recognition is an approach which gives photonic designers ease of mind that their designs meet verification requirements before fabrication without hours of setup. LVS, or layout versus schematic, is a method of physical verification which checks whether the layout matches the schematic it was derived from. LVS is crucial to ensuring the circuit will behave as the designer intended and verified with simulations. The results of LVS will show a comparison of nets and pins between the layout and the schematic, as well as calculations of the geometrical properties, such as radius, width, and parameter. The primary challenge of PIC LVS verification is simply the immaturity of the ecosystem compared to the electronics world. This makes classical approaches to LVS much harder to perform, like extraction of devices from the layout, characterizing such devices with their geometrical parameters, and comparing them to those in the source. Electronic integrated circuits uses basic components, which are treated as built-in devices. However, photonic integrated circuits do not yet have supported devices which LVS can use. Verifying connectivity is another challenge. In a PIC, the assumption that all interconnects are wires with no dimensions or parameters is not enough to ensure proper optical connectivity and behavior. Waveguides need to be treated as devices since their properties will have an impact on the operation of the circuit. The marker shape recognition approach is Calibre's answer to these issues. In the marker shape recognition approach, dedicated marker layers are used for the detection of devices. Markers are used for device recognition and parameter extraction. To add a new component to the rules file, first pin definitions are created. Then the seed layers are extracted to a defined marker layer, which tells Calibre the structure of the device. Structure-dependent derived layers are then calculated, which will be used in parameter extraction. Using the DFM property function allows the necessary properties to be defined and used in the device template. The device recognition section uses the previously mentioned sections to create a device statement, taking in the seed layer, pins, and properties as parameters. Functions are used within the device statement to calculate device properties to be checked against the source. Finally, property tracing is added to define a tolerance between the source and the layout, which needs to be passed in order for LVS to pass. Here is a photonics layout. The top level cell contains optical devices such as a 90-degree bend, direct coupler, grated coupler, waveguides, ring resonators, and tapers. These devices do not have LVS models, so the marker shape recognition approach was used. Calibre LVS is integrated into LEdit. Launch LVS with the top level cell active. Include the rule file with the marker shape recognition. Opening Calibre with the top level cell active will automatically populate the cell information in the layout field. The source information can be included from either a netlist or a schematic. LVS can now be run. The smiley face indicates a successful run and that the source matches with the layout. To check the results in more detail, Calibre result viewing environment can be opened. A comparison of nets from the source and layout is provided. The values of each device can be checked by opening the schematic pane. Checking the Bend 90 device, it is apparent that the values are within the 3 nm tolerance set in the rule file. Calibre's marker shape recognition approach to LVS is a powerful way for photonic designers to rest assured that their layouts match the expected source when moving forward with fabrication. Creating new device definitions is simple, effective, and scalable, and will help designers feel confident that their layouts are as they intended.